As set2 with addition is a group, right? We are talking here about the pairs of integers and m, and the addition, as pq, for instance, is equal to n plus p, m plus q, okay? This is a group, right? The neutral element of this group is 0, 0, and the inverse is, of course, the inverse of nm is equal to negative n, negative m, right? So this forms a group. It's an additive group. It's commutative, right? Because this operation is commutative. So this is set2 with plus, right? Set2 with plus. Set with plus is, of course, another group, right? And we're talking here about a function that maps this group into this one, and the function is defined this way. So this f takes any element in set2, x, y, and maps it to an element of set, which is just the addition of these two integers, right? Okay. Now we have to prove a few things about this function f. Among them, we have to prove that this function is a homomorphism, and then a few more. So let's begin with that, right? So let me erase this, which we're not going to need anymore, right? So let's begin with proving A. So remember what is the property that defines a group homomorphism. The group homomorphism maps the product of the first group into the product of the second group. So in other words, if you take f and you apply this f to the sum of two elements of this group, let's say x1, well, the two elements are going to be this and this, right? And we are going to calculate the sum of these two and apply the function f to this sum. So what we have is this is the sum of the two elements, right? y1 plus y2, okay? And of course, the sum of these two is equal to, according to the rule, is just x1 plus x2 plus y1 plus y2, right? Okay, but we can group this like this, okay, plus x2 plus y2, and this is equal to f x1 y1, and this is equal to f x2 y2. So you see, the function f maps the product in the first group, which is the sum, into the product of the second group, which is the sum, right? Okay, so this is a group homomorphism because it satisfies this property, right? Now the second thing we need to prove is that this, well, the second thing we need to do is to calculate what is the kernel and the range of f. Well, let me begin with the range because it's easier, right? The range of this is just set. The reason is the range would be all the integers such that can be decomposed into the sum of two integers, but that's virtually any of them, right? Any integer can be decomposed into the sum of other two. So any integer is the image of some pair of integers in this other group here, right? So the range is set, okay? That's easy. Now the kernel, remember, the kernel is the set of elements in the group, let me put it like this, a set of elements in the group such that f of g is equal to the identity of the second group, right? Okay, so in this particular case, what we're talking about is what is the set of x and y's, integers, pairs of integers, such that the image is the neutral element of the second group, which is just 0. And since this function is just the sum, the condition is that that y is equal to negative x. So in other words, the kernel of this homomorphism is just the set of pairs x, negative x in set 2, where, well, let me just put it this way, set the pairs of these elements x and negative x, where x is any integer, right? Okay, so that's the kernel. All right, let me erase this now. Okay, and now we go to proof C, right? So C is, we have here a kernel, right? And we have to see which of these elements belong to this. Sorry, we have a coset here. We have the kernel. The kernel, you know, is a subgroup of this group here, right? Sorry, of this group here. Okay, and this is a coset, right? Because well, it's the right coset, but actually it's right and left coset because this operation, both operations are commutative. So these are two abelian groups. So it doesn't matter whether we're talking about left or right cosets. But anyway, this is the coset, the right coset of the kernel, right? With 2, 3, this particular element, right? And we need to know which ones of these elements belong to this coset, right? So we need a better characterization of this coset here. So let's see, what is the kernel of F? Well, we have just found that the kernel of F is just all the pairs of elements like this, x negative x, where x is an integer, right? So if we add to this kernel, we add 2, 3, what we have is all pairs of the form x plus 2 negative x plus 3 plus 3. All right. Okay, where x is an integer. But there is a better way of rewriting this, okay, which is it's going to be more convenient. And it's if we add these two elements here, right, what we get is 5. So another way of expressing this is saying that this is all pairs in set 2, right, so pairs of integers, such that the sum is equal to 5. 5 is just the sum of these two elements. So in general, the kernel plus AB will be the set of pairs in set 2 where the sum is equal to A plus B, right? That's generally how we describe a coset of this kernel, right? So in this particular case is this one. So all we have to do is to go through all these pairs and check for which ones the sum of the two components is equal to 5. And we have just two, this one here and this one here, okay? The other two are not. 3 plus 3 is 6, and 0 plus negative 5 is negative 5. So these are excluded. So only these two elements belong to this coset here. All right. Now the next question we need to answer is whether is for D, right? We need to figure out whether it is true that the sum of these two cosets is equal to this coset here, okay? All right. Well, as I said, this kernel here is, well, sorry, this coset here will be equal to the pairs of set 2 for which x plus y is equal to 5, right? All right, or written in a different way is all pairs of the form x plus 5 negative x, right, where x is an integer, okay? Because this is the general way to express all the solutions of this equation here, right? Okay. Yes. So this is this one. So the coset of -1, -2 will be similarly all the pairs of integers for which the sum is equal to -3, right? -3. And those are the integers of the form, or the pairs of integers of the form x minus 3 minus x, right? Because if you add these two, you get just -3. okay, where x is any integer, right? And finally, this one here, kernel of f plus 2, 0 is equal to same story, where here you have 2, okay, which is the sum of these two, and those are the integers of the form x plus 2 negative x, okay, where x is those, right. Okay, so if we add any element from this and any element of this, so let's take an arbitrary element of the first coset and an arbitrary element of the second coset, what we get is x plus x prime and 5 minus 3 is 2, okay, and here we get minus x plus x prime, okay, is minus x prime, which is equal to that, and that is of course an element of this coset here. So the sum of any element of the first coset plus any element of the second coset gives you an element of the third coset here. So this is true, okay, and the idea that this is true, and of course that you can generalize that, right, in the way that if you add, well, you have 2, 3 here, right? 2, 3 and 5, 0 belong to the same coset, right? Here you have -1, -2. This one and -3, 0 are in the same coset. And if you add these two, you get 2, 0, and 2, 0 is in this coset here. The fact that this is true for any pair of cosets that you have here, so if you make appropriate choices of the element, an element here and an element here, you get an element of this one, right? Says that if you, well, says that you can extend the sum, right, to cosets, okay? So what we are adding here is cosets, so equivalence classes, right? Okay, if you can do that, then you can answer the next question, which is E, and is how to extend this group homomorphism to an isomorphism. And the reason is, well, the extension that you had to make is you just take F as, well, let me, you can call that isomorphism phi, which maps Z2 over ker F, right? So the quotient group into just Z. And the mapping is, you take any class here, well, let's say the class of Zn0, okay, which is all elements of the coset for which the sum of the two components is equal to n, right? And it maps this to n, right? This is of course a bijection, and this is an isomorphism of groups. Morphism of groups, right? Okay.